So, it's my pleasure to welcome David Brebner, quintessential successful Kiwi entrepreneur. Does it fit? Good man. So, good friend of Multicore World, please pay attention. You won't be disappointed.
All right, so we've got a few different topics today. Accelerating machine vision and general computation tasks with Sparsity, and then I'm going to dig into some Vulkan and SPIR V examples. I think they're quite interesting, and specifically as they refer to memory, which has been a big topic. Those who've seen my previous presentations know we've spent a bunch of time with acceleration frameworks like SYCL. The benefit of SPIR V is you're right down at the GPU level, so you get some extra wins. This is an example. I've just been in Europe, so I apologize for my tardiness in arriving here. This shot on the left-hand side is a 4,000 by 3,000 pixel image of the side of a vehicle. There's about 200 images captured in a scan as the vehicle passes through the system. It's about 2 gigabytes of raw data that needs to be processed right there and then. And if you're producing a lot of cars, that quickly becomes exabytes of data. So you don't really want to store all of that. You want to process it, and you want to use the information in it to solve your quality problems and really just keep the bits you need to improve the machine learning models that you apply on top. Now, there's a lot of esoteric architectures for AI, some of them extremely interesting, some really cool new tensor processors and neural processors, and the company that Grok with a Q that got bought by NVIDIA, super interesting with their essentially pre-timed architecture, so everything just flows without need for clocks. But in this case, GPUs are really ideal because the same reason that they're good for rendering graphics, they're good for doing the inverse pipeline as well. So they already have things like trilinear sampling and a lot of graphics-oriented processing. I apologize, this is a bit of an eye chart, and it's probably a bit hard to see with the lighting, but across the top is the left-hand side of the car, across the bottom is the right-hand side of the car from different lighting directions. So that's kind of looks like a kaleidoscope, but that's kind of the unpeeled set of images that are captured by the system and then need to be processed essentially in a few milliseconds to generate the 3D normal maps and the other photometric data we use for AI. So I'm going to talk specifically about intrinsics and wave intrinsics. So intrinsics being operators over a set of pixels, which is a horrible thing to do in general, because we have multiple images captured and those images have correspondences and we want to sample across that whole set of images. And the idea of the wave, or otherwise known as a subgroup, is you can basically have the GPU keep all those coordinated, so the access to the memory of those images is synchronized to the kind of pixel area that you're currently sampling. The big challenge there is how we deal with things like if statements. So as soon as you start dropping data out, which is the goal is to not process all your data, GPUs don't like that. So we want to have wave intrinsics, but we want the benefits of having sparsity or conditionals at the same time. So there's about 32 to 64 threads, depending on the type of GPU we're using. And under the hood, it's actually using a crossbar switch or a shuffle network. So when I talk about the memory, what's really interesting is it's not going back to the GDDR5 or the HBM memory that's in the GPU. It's basically saying, hey, I've got this in my wave intrinsic buffer. I've got it over here in my other core, in my wave intrinsics buffer. And it basically shuffles it between those registers. So it's extremely fast. This is running on my local GPU. It's a bit of an abstract concept, but this is basically a summing of a whole bunch of sine curves that are running across 64 threads. So when I have all of the threads enabled, I'm getting my full 0.1 trillion operations a second of computation. And as I drop out some of those threads, and now I've got a sparse scenario, that's an 89% stall or waste scenario if I wasn't running wave intrinsics. So in essence, instead of the GPU doing the same exact work it would have done with a full buffer, Now with a reduced buffer, I can actually gain those benefits back. So I can now have more computational tasks to do on my GPU. And just to give you a sense, it's definitely not as clean as things like SYCL or OpenMP. You're diving into the weeds here because this is kind of like an assembly language, and we're looking at a readable representation-ish of those calls. So what we do is we define some storage buffers and then the accessible group memory for those storage buffers. We set up a dispatch, so we're going to dispatch a whole bunch of threads. And we say we want these intrinsics or these subgroups to operate over these waves. So in this case, we want a min, max, a sum, and a count. And then what's interesting is that those come back in sort of an ad hoc fashion. So we don't actually control that process. That all happens non-deterministically depending on your particular driver set and your particular GPU. But what we do is we create a lock on the right-hand side there around those group shared variables. So those will come back to us and end up in our min data, max data, sum data, count data structure. And then it's a bit of a hack, but the way it's done is we basically say if you're on the first count of the wave, that's the one that's going to communicate back to the CPU. So that's how we actually pull that subgroup data back out. So you can think of this as group reduction, global atomic data access, and basically there's this specialized hardware that communicates inside the registers of a GPU. And so this gives us around about a 64 times speed up, plus also a 64 times reduction, depending on how much you're decimating the data. But it's not often you can get those kind of improvements. And that's largely due to the fact that you're not just computing everything you don't need, and also that you're now drawing a lot less data from memory, or you're drawing it in once when it first comes into the buffer, and then it's handled in memory. And to give you a sense, if I zoomed into one of those images that you saw on that big 200 image panel, that little red box, if we zoom into that red box, so it's about as big as a piece of tire tread, so it's about 4 millimeters long, and that's a scratch that's broken up into 3 parts. There's a slightly bigger scratch at the top right, there's like a small sub-scratch that continues on. And the cool thing is the 3D shape of that tells us exactly the depth of that scratch and how big it is, obviously its length. And speaking of stuck in the snow, one of the side effects of snow in Europe is they'll often, and certainly in Germany, they put salt on the roads. So this is one of the cars that we were scanning, and it had come in from outside. The salt had essentially ended up on the surface of the car, and there were little water drops running down the side because the snow melted and carried the moisture down. And what's really amazing in the right-hand depth view is we were still able to precisely measure the door gap, and we could actually see things like scratches and chips through that salt, because you can tell the salt is coming towards us. It's lit from the top and the bottom, whereas a chip or a scratch is lit from the bottom and the top. So the light angle tells us the direction, the 3D direction of the object. I'm going to talk a little bit about anomaly detection. So one of the big challenges is essentially the training problem. So for manufactured goods, the types of defects you get can be completely random. Someone's accidentally walked past and scratched something, taken a chip, taken a gouge, I don't know, there's a fracture, there could be bubbles in the paint. There could be literally probably 1,000 different classes of potential defects. So it's not really a good way of doing machine learning. So instead, in this case, we're doing the reverse. What we want to do is to do anomaly detection. We want to say, what's the perfect car? And if there's anything that's different, show us in a heat map. So this is there's a series of papers on this topic, but this is a recent one around the Dino V3 models. And the idea is you train a model that knows the variation. So for example, the outside of a car will have very little variation, whereas a seat that maybe has organic leather in it would have higher variation because the pores in the leather would change. And what it basically does is it learns. So in this case, it's learned a flat aluminium card. And in this case, this card has the paint has flaked. And in the card on the right, it's been impacted. So it's slightly dented in. There's actually a second point dent up slightly to the right, which you can see in the heat map much more clearly than you can see in the normal map. So this is the first pass we do on our detection. And this runs in just a few hundred milliseconds. So the idea is we can scan a manufactured item. Within a few milliseconds, we can identify any hotspots where there's something that isn't supposed to be there. Interestingly, we actually train that on the CAD data. So we use a full digital twin using an Omniverse 3D model. We pre-render what the perfect thing should look like, and it's quite confusing because in some cases, some production lines produce up to 1 million variations or more of a given manufactured item. So for example, if you were to order a car online, you can choose all these different, wings and spoiler kits and everything else, and by the time you count all those permutations, it can be a very large number. So this is a simple example, but you can imagine even with more complex examples, we can basically have a pre-trained model, we find and isolate the anomalies. And then from there, the next stage is defect classification. So the idea here is we look at that defect and we say, in this case, this is a ripple defect. I think one of the other really interesting areas which is starting to create a little bit of opportunity in the market is historically we've been focused on GPUs because a lot of what we've been doing has been image processing. And GPUs are not bad at doing some of these anomaly and classification tasks. But this is a little bit about the new Panther Lake CPU from Intel, and anyone who's familiar with the big bets that Pat Gelsinger made, most of them paid off, which is pretty amazing. Not good for him, but good for Intel. So backside power is a huge deal. So that's freed up the data layer to have a lot less noise, and it's enabled some incredibly, they're almost competitive with an M5, which nobody was really expecting to happen in one generation. But in particular, the NPU is really interesting. So the Arc GPU is now pretty good. It's pretty decent for the task we want. But you've now got a pretty decent 50 TOPS NPU. And so when you're doing those inference tasks around defect detection, it turns out to be really, really good for that. I'm going to talk a little bit about the light revolution nanoscope or nanoscopy. I think I've briefly mentioned this on prior talks. This is what a slice of an embryo looks like on the right-hand side. So we end up taking multiple images through a stack, which enable us to look at things like, in this case, bovine embryos, and find tons of interesting details that morphology correlates, for example, with embryo grade quality. And it's essentially two types of sparsity which we're leveraging. So standard wide field white light microscopy uses a Kohler illumination system at the bottom, which is basically a big diffuser that creates light coming from every direction. And that was very much intentional. The idea when that system was developed, and Zeiss and Abe and all those guys were working on this stuff, was to effectively cancel out things that are out of the focal plane. So everything else just kind of gets blurred away. And the distinction here is that we have a sparse illumination source. So we have something that's very close to a point source. LED isn't quite a point source, but it's close. And just like with photon tracing for reflection, for refraction, same principle applies. So if any light got to the camera, the only way it got there was from that one point source in the entire universe, and it ended up going through that sample and being refracted, diffracted, a little bit was absorbed or reflected. And then the other benefit of this is that it's not a light stars situation. So there's basically a very small LED pointing straight into the camera. So this can run at very high speed compared to normal kind of microscopic setups. But the second part that's really interesting is the sparsity of subject. So depending on what you're imaging makes a big difference to the trade-offs in having a point source. So for example, if we're imaging something like a sperm, it has a tail, a flagella, and that is very small. So that gets down to below 100 nanometers in width. And according to the principles of microscopy, you shouldn't be able to see that kind of thing because it's well below the limit of the frequency of light that we're using to illuminate the subject. But we have the benefit that it's basically in a medium, in a liquid, and there's pretty much nothing else nearby. So what's really cool about that is, yes, we couldn't use Rayleigh's criteria to separate 2 points, but if you've just got one sperm or a bunch of sperm, but they're individually in their own space, we can pick up and reconstruct the gradient that is the flagella of the sperm. So we can actually see well down into the nanometer range. So just to give you a sense, the specular setup, we're looking for reflection. In the case of the photon tracing for refraction, the LEDs point basically down and they're off-axis and they go through the subject into the microscope. So it's incredibly simple compared to a normal microscope. All of the work is done in the computation. So the actual light array has multiple LEDs in multiple axes. So you've kind of got a north, south, west, northwest, etc. Configuration. And then on the right-hand side, you can see what actually happens, which is pretty crazy. If you have a sample which is three-dimensional, as the light goes through at different angles, it goes through different molecules. So actually what ends up on the camera is a rotation. So we can literally rotate an embryo without moving it. All we do is we move the point light source above it, and we're actually looking at different molecules in that subject. And then computationally, we can recover the focal plane. So down below it shows how when you imagine those individual sets of images with the different off-axis lights, what it means is the focal plane doesn't move, the center of the slice that you're looking through doesn't move. All the other stuff rotates left or right, depending on the way you're moving the LEDs, or right and left if it's left and right if it's underneath the focal plane. So we basically remove all the stuff that moves and we can pull out the focal plane programmatically. And just to give you a sense of it, we had a number of animal husbandry specialists very confused by the extra information they can see. So you can see here, there's like a little pigtail curl at the end of that sperm, and that's what's known as the end piece. So it's the part of the tail that's past the axial filament. And you can see it in a scanning electron microscope image, but you shouldn't be able to see it in a light microscope because it's much too small. But as I say, thanks to the sparsity of the light and the sparsity of the subject, we can still pick up that curling tail as a gradient. So it's still recoverable information. Oh, I'm getting close to time. All right, here's just a crazy one for everyone. So this is a nucleotides. So the goal here is, can we have an alternative model of a complex physical system, or system from physics? So in this case, it's a geometry-based model to create a digital twin so that we can look at decay rates and isotopes without having to simulate quantum states. So the goal here with this sparser and simpler representation is to generate about 1 million times speed up. If you're familiar with lattice QCD, that's a common solving framework for simulating quark and gluon interactions. It's very complicated. 10 to the 23 possible quark states need to be summed for a simulation. So there's a lot going on there. My friend Tracy McSherry, phase-space, which is the geometric algebraic representation of 3D space that he's using. The idea is to instead look at essentially a soliton representation, so basically treating an atom as a field. So instead of 19 to 23 parameters, which are a whole bunch of constants, most of which we don't know or know how they're derived, there's actually only one constant, which is the fine structure constant. So that's the good old 1/137, which no one really knows why it's that. But you can think of that as Arnold Sommerfeld described it as the strength of the electromagnetic interaction between elementary charged particles. So that was then measured, I think, it was actually measured prior to that in about 1870, but that's the name it's given now. So then beta is the fine structure constant derived from that. It's got a precision of 0.0023% to simulation. This is the nucleides table, so if I bring that up. So these are the stable atoms. These are the negative beta isotopes, positive beta, alpha. And then if I go to recalculate these, so it takes about probably a couple of days of HPC time to compute iron, 108 isotope, because it's a very heavy isotope. So that's recalculated all 4,000 nucleotides. that little Python script just then. So it's pretty interesting. And the main reason it's able to do this is because the model appears intractable, but it's been separated into basically 3 subgroups. So there's 3 different types of stable solitons or standing waves. So I think, who's to say how closely this models reality, but I think the idea of creating physically simulatable models where you are performing simple calculations rather than trying to simulate and sum very complex interactions clearly has a huge potential, given this is more accurate than a lattice simulation. So, cool.